This is section 3.3, page 6. Suppose that u and v are functions of x. So these are like g of x, h of x, but instead of function notation, we just use a single letter. They're differentiable at x equals 2, and we have some function values at 2, derivative values at 2 for each of the functions u and v. We want to find the following derivatives when x equals 2. So since it's differentiable at x equals 2, there's not going to be any issues about corners or discontinuities or anything like that. Basically, this is just practice with your differentiation rules. So the first one says the derivative of u times v. This is going to require the product rule. So the derivative is just equal on the product rule. First function times the derivative of the second. So we'll just show this derivative notation, v prime, plus the second function times the derivative of the first. So that basically looks like the product rule. And at this point then we just substitute in the values. So u at 2 is 3, v prime is 2, v is 1, and u prime is negative 4. And then just continue evaluating. This is 6 plus negative 4, so that's equal to 2. Change the screen here. Okay. Next one, we have, we're asked for the derivative of u divided by v. So we're going to need the quotient rule. Actually, I'm going to go over here and write product rule, quotient rule on this one. So in the quotient rule, we always start with the bottom function. So the derivative is v, and you want to start with the bottom function, not the derivative, just straight up the function. V times u prime minus, is what's always used in the quotient rule, minus u times v prime all over v squared. Now we'll evaluate this from up above here. The v value at 2 is 1, u prime is negative 4, minus u is 3, v prime is 2, all over v squared. V is 1, and we'll square it and just work this out. We got minus 4 minus 6 over 1, so that just equals minus 10. Okay. Here's another quotient rule for part C. Same thing, but just the reversed functions. So on this one, remember, start with the bottom. So we get u, the bottom, times the top prime, v prime, minus the top, v, times the bottom prime, u prime, all over the bottom function squared. We'll substitute in these values. U of 2 equals 3, v prime was 2, minus v is 1, u prime is negative 4, and that's all over u, which is 3 squared. Don't forget to do the denominator part. It's a common thing to leave out. In fact, I just did a second ago. Had to go back. So here we go. We get 6 minus a negative 4 all over 3 squared is 9. So this is equal to 10/9. Okay, finally in this set, we have the derivative of this. Looks a lot like a polynomial, but this is, we will need the product rule here. We don't really need the product rule for this part. If you think about this, this is a function 3 times a function u. So if you just did the derivative of 3u using the product rule, think about that, what that would yield us. We would take the first function times the derivative of the second, plus the second function times the derivative of the first. The derivative of 3 is just 0. So this whole piece goes to 0, and the derivative of 3u ends up being just simply 3 times u prime. So the coefficient like this basically just comes along for the ride. We do need to remember, though, we need to consider u prime. So the derivative here is not just 3, because we do have this function that has some derivative to it. We don't know exactly what that function is, so we just denote its derivative with u prime. So let's employ that technique there as we go through this problem. So the derivative of 3 times u is just equal to 3u prime, minus the derivative of 2v, same principle, this is going to be 2 times v prime, and then plus 2uv. So there's a couple ways you can approach this. You can bring this 2 out in front and then just use the product rule for u times v, or what I like to do sometimes is to use 2u as its own function and then v as the second function and apply the product rule there. So that's what I'm going to do. I'm going to do plus, and I'm going to go ahead and put brackets around this so I know I'm going to isolate this product rule here. So for the product rule, I have the first function 2u times the derivative of the second v prime plus the second function v times the derivative of 2u, which is 2u prime. Now there's no negative signs here, so I don't really need these parentheses. I was just using it to isolate this whole derivative. Alright, so now we can plug these in, plug in the values from above. We have 3 times u prime is negative 4, minus 2 times v prime, which is 2, plus 2 times u, which was 3, v prime, which is 2, plus v, which is 1, times 2 times u prime, which is negative 4. And evaluate. Minus 12 minus 4, that's plus 12, and minus 8. So I can see that minus 12 and plus 12 are going to cancel. All I have left is minus 12. Okay. In problem 8, we're asked to consider this polynomial function, and we want to determine the coordinates of the point where the function has a horizontal tangent. So if we think about what this function might look like, it's a cubic function with a positive coefficient. So somehow, perhaps it looks like this. And we want to know where we have a horizontal tangent. So if you think about it, the horizontal tangents are going to show up where you have a low part and where you have a high part. So on this, I'm anticipating two horizontal tangents. And with the horizontal tangent, you think about that as its derivative has to equal the slope of the horizontal tangent, which is 0. So the technique here is to determine this derivative and set it equal to 0 and solve for the points that make it 0. So let's do that. F prime of x is, this will be pretty easy to get, it's going to be 6x squared minus 2 times 7 halves is just 7, x to the first power minus 5. So that's my derivative, and this is what needs to equal 0. I want to know where the first derivative equals 0. So I'm going to solve that, find the zeros of that equation. So perhaps it will factor. You should always consider that. And so you can do some trial and error. If I put 3x and 2x, and my right hand side is going to be some sign of 5 and 1. If I put 5 here, I'm going to get 10 there. I'm going to go with this. So I have 10 in the center, 3 on the outside. I need it to be overall negative, so this is going to be 3x minus 5, 2x plus 1. That equals 0. And using my zero product property, one of my favorites, I get 3x minus 5 equals 0, and 2x plus 1 equals 0. And if I solve both of those, here I get 3x equals 5, or x equals 5/3. Here I get 2x equals negative 1, or x equals negative 1/2. So I have two x values, two locations where I'm going to have horizontal tangents. It asks for the coordinates of these, so I'm going to have to figure out the y values. And when I'm figuring out the y values, I want to plug in these x values into the original function, not my derivative function, that would just give me zeros. I want to put it in my original function. So for me, the nicest way to do this with my calculator. Okay, so I already have the function in there. There's a couple ways you could do it, so I'll show a couple of ways. I'm going to just graph what I have here. there's my graph, and I can use second calculate. I could use calculate zeros, and that would give me my x and y coordinates, but I'm going to just, right now, just calculate the value. I'm going to put in 5/3 for my x value, and it will show me my y value. So I'm going to just jot that down here. I'm not real excited about it being this kind of weird decimal. I would kind of like to have the fraction equivalent of that. So I'm going to show you another way to get this. But that would be one way to do it. And then you could plug in second calc value, -1/2. But what I want to do is show you this other way to do it. So if you go to the main screen, I can use function notation to do this. So I'm going to select y1, and using function notation style, I'm going to put in 5 divided by 3. And I get that same value. And now what I want to do is convert that to a fraction. So hopefully this will come out to a nice fraction, and it does. 313/54. And I'm going to do the same thing, alpha f4, and I'm going to put in -1/2. And I get 4.375. Again, I could use that decimal, but I'm going to change that to a fraction. I get 35/8. There you go. Actually, I could get a graph, a fraction immediately if I input my value in fraction form. So if I do alpha f1, I put -1/2 already in that fraction form. And when you hit enter, it automatically comes out in fraction form. So that'd be a way to get there without taking that other math 1 step.